Hi, my name is Somu. I'm from Amazon. I work in Bedrock now. Until a year ago, I was in Dynamo, building a bunch of replication services, specifically regional and global. In this talk, I was asked to give this talk like 2, 3 weeks ago, and I've been lazing around preparing for this talk. But I thought, okay, I'll talk to you guys about how we build global tables and what is the thought process which went into us building global tables, and give you a small demo of how things work and what is under the hood for global tables. If any of this content is like familiar, just let me know. We can skip over the slides because it's already like 7 o'clock and I don't want you guys to stay long. So we can kind of skip some of the slides. A quick primer about Dynamo. Dynamo was built as a highly scalable and highly available key value store. To scale Dynamo's tables horizontally, we just kind of partition the data across multiple storage nodes. To make it very highly available, we kind of split data across 3 availability zones. And now we have to replicate data across 3 availability zones for the same table. We use a version of multi-pack source, and this allows us what this does is selects a leader in one of the availability zones. So when you make an update item call, it goes to the request router. Request router does the admission control, authorization, authentication, and then looks up, hey, where does this key belong? And then picks one of the 3 storage nodes to say, hey, can you access this data? And if that storage node is not the leader, it's going to point you to the right storage node in the right availability zone to go write that data. The leader receives this request, generates a log entry. The log entry is replicated across those other 2 storage nodes. Once 2 out of the 3 say, yes, this is durably committed log, we acknowledge to the customer saying it's successfully stored. Now, this is like the high-level view of how things work, and a single update item works in DynamoDB and regional DynamoDB. And the reason we build it to be highly available is to endure failures such as single AZ going down or node failure, so that we have very high availability in terms of what we're building for a key value store. And being able to shard across multiple storage nodes gives us the scalability which customers will look for in terms of like how much data you can store and without losing the performance. And that was a key thing which we were always looking for, because as data size grows, you can see some of the databases actually slowing down. And in Dynamo, we didn't want to kind of do that. We wanted to kind of build a system which is scales for storage, but you don't lose the performance as you kind of scale for storage. So a couple of key tenets in Dynamo is like having predictable performance and having seamless scale. I think these were 2 things which we always ingrain in Dynamo. Is like these are two of the most important things we build into every feature. And Dynamo supports 2 consistency modes for reads. One is eventual consistency, and the other is strong consistency. Eventual consistency basically says that, hey, you can read a copy of not all your replicas will converge to your write immediately. Some may take some time to converge. So if you read from those replicas, you could land up getting a staler version or older version of your data, right? This is super critical. This is super critical for some applications which are really not which really don't require strong consistency. For example, if you're watching on ESPN the score of a game, you really don't need strong consistency. You don't need to kind of have this score immediately as soon as it's updated. You could live with the score which is 5 minutes old or a minute old, unless you're a diehard football fan. But so in Dynamo, when you make an eventual consistent read, the request router routes the request to one of the 3 replicas. It doesn't care. It just says, hey, I'm going to route it to one of the replicas. Just give me what the data is, right? Because it doesn't care if the data is actually converged to the latest write or not. The replicas converge to the storage node has the latest write or not. The other mode Dynamo supports is the strongly consistent reads. And strongly consistent reads are for applications which really need the latest version of the item to make any progress. For example, control planes. If you're making any changes to control planes, or you kind of depend on your control plane would depend on the latest state of some resource in your system, then you need a strongly consistent read. So Dynamo supports strongly consistent reads as well. And how do we implement strongly consistent reads? Strongly consistent reads go always to the leader. Because we know if the leader has accepted write and we've acknowledged it, you can always going to get the latest write from the leader. So strongly consistent reads go to the leader.
Can I ask a quick clarifying question? Is that the leader going to be like that availability zone for all the keys, or is it like on a key by key basis? Like this key might have a leader here, and that key may have a leader in.
Good question. I think leaders can be anywhere across any availability zone. And Dynamo shards a table into continuous key ranges. So for a bunch of keys, which that particular storage node hosts, it would be the leader.
Okay. So It's not one key per.
No.
It's smaller than the entire availability.
Yes.
Thank you.
If anybody wants to read a lot more about the consistency models, I would ask you to kind of take a look at Doug's paper, where he talks about data consistency through baseball. If you're a diehard Indian fan, then Akshat has written one with cricket, using cricket as an example. But definitely, Doug's paper is super interesting, and him using baseball kind of tells you different kind of consistency modes which databases can expose and where they are very useful, right? As application developers, we always think as that strongly consistent is the only way to build systems. If Khwaja were here, he would tell you that eventual consistency is good enough in Dynamo. And the reason is that in most cases, Dynamo's replication is so fast by the time, because 2 out of the 3 storage nodes have to tell S before it can commit data. So 66% of the time, your eventual consistent reads would land up being strongly consistent no matter what. And the replication is so fast that the third replica would also have the latest data by the time you make a round trip and come back to Dynamo, right? Now, given the fact that Dynamo is built across multiple availability zones, with withstand availability zone failures, we still had customers asking us about multi-region setups. They wanted to go build multi-region data. They wanted data stores in multi-region because they had a lot more stringent requirements on availability and continuity of the business operations, right? Because no system is immune to failures, 100% failures. You can have hardware failures, you can have software failures, you can have a deployment go wrong, or you can have something else go wrong, and then so yeah, if one of the region experiences problems, then you definitely want to shift your traffic away to another region and kind of be able to continue your business operations, right? But this continuity of operations has 2 key elements. One is recovery point objective, and the second is recovery time objective. Recovery time objective is slightly easy to kind of think about. It does how soon do you kind of recover from your failure, right? It's a mean time to recovery, mean time to repair, right? You can call it with other names. So this kind of defines how long you're going to be down and how quickly you're back up and running. The first one is the recovery point objective is what kind of tells you how much data can you afford to not have when you fail over to the new region, right? Do you need all the data? Do you need the last read which was acknowledged in the region, or can you lose data which was like 5 minutes worth of data? Different applications have different requirements, and that defines what continuity of your business applications is going to be. There may be some customers who say, "Okay, I can lose 1 day worth of data." There may be some customers who can't lose even one single write. And at the same time, when a lot of the application developers are kind of thinking about multi-region setups, there are 2 things which go hand in hand. One is the cost versus resiliency, right? I store backups all the time, but I never restore from backups. Backups are a very cheap way to kind of have disaster recovery as a disaster recovery option. And backups also allow you to kind of recover, but it takes a long time to kind of recover from a snapshot. Like I had a friend who was telling me that the 16 terabyte restore was taking like 5-6 hours before his business could come back online. So backups are good, cheap, but the recovery time objective is going to be really, really high. Likewise, you could have something where you have a warm replica which you kind of do not use at all, and write data to it from time and again. It's going to be low cost because you're not doing the reads. You're just kind of keeping regular snapshots and keeping it up and running, but you're not using it at any point in time. Or you can have an entire sort of a warm standby, like a DynamoDB global table with a multi-region replica, where the other replica can do all the reads and writes which the other replicas in other regions do. This to give a little bit of history. Dynamo, when we kind of started implementing global tables, firstly, global tables is work of a whole huge big team, just not my work. This team of smart engineers, the team of smart engineers like Kenny and Akshat, who set up the groundwork as well. Kenny set up a bunch of the groundwork for global tables by implementing logs and CDC for Dynamo back in the day. Then Akshat and I worked on a bunch of global table stuff together as well. So when we started implementing, one of the key things we were asking was, what are customers using this for? Customers are using this for disaster recovery. They wanted high availability, and they wanted the same performance as regional DynamoDB, right? So the first one we implemented was asynchronous global tables. We also saw customers implementing this by themselves using libraries. And it's really hard to implement this. I'll go into details why it's hard to implement using a library. But we did, as soon as we all implemented update streams, the first things customers did were like, hey, we're going to use this to kind of build replication, cross-region replication. And it's very hard to get that protocol right. So everything in Dynamo depends on the replication log the leader generates. Leader of partition generates and replicates regionally, right? The log is the database for us, and this is what even Peter was referring to about a couple of years ago in reInvent. The log powers backup restore today. It powers update streams. Update streams powers Lambda triggers, which I use frequently, but I don't know how many of you use it very frequently. But update streams also powers Lambda triggers. It powers asynchronous global tables. How does it power asynchronous global tables? We have a small replication engine which sits outside Dynamo actually, and takes all the change data capture and replicates it to another region. On the outside of it looks like a very easy problem to solve, and we did think it was a very easy problem and we can solve it outside Dynamo. But one, it gets very complex quickly, and two, it gets very inefficient quickly as well, because you have to solve the problem of, there are two problems you have to solve. One is replication, and one is how do you deal with write conflicts, right? Today's async global tables also does not have any limits on how many replicas you can have. You can have n number of replicas, n number of regions in a asynchronous global table, and the replication engine for each region pair is individual. We built it this way because we again want every pair of regions to have their own high availability. Want it to be highly available. So every pair of region gets its own replication engine. So even if one replication engine has stalls because a region does not take any writes, the other replication engines can keep chugging along. They don't have to worry about one region being down or one table not being able to take updates. This diagram goes over a timeline from left to right. There are 5 regions in this particular slide. Write happens in region R1. Once the write is successfully said yes to the customer, the write is replicated asynchronously to the other regions. The only guarantee is the write will get replicated. There's no guarantee that they will get replicated at the same time. So each region can land up seeing the write at any given point in time. Right? Now, on top of that, the replication is bidirectional, right? And the replication is bidirectional across all regions. So if you have a 3-region pair, then you have like 6 ways of replications going around. Strongly consistent reads are strongly consistent only in that region. So if a region has accepted a write, you can definitely see the writes in that region. The other regions, if you perform a strongly consistent read after writing in region 1, the chances are you may see or you may not see the latest write which happened in region 1. Right? But you will land up seeing that write at some point in time, eventually. Right? And that's why this is asynchronously synchronized regions. If there are 2 writes happening to the same key, then we have to solve the problem of write conflicts. Which write should persist over the other write? Like, because 2 regions don't know the writes are happening to the same item, how do we decide to resolve this conflict? We first tried it externally by saying, hey, we will store timestamp with every item, right? Every item is timestamped and has its own region. When we built the library, we kind of took the same idea. So we stamp every write which comes into Dynamo for a global table with some metadata which says at what time did this write happen and what region wrote what region is this write originating from. Now, if there are 2 writes which happen at the same 2 writes happen to the same key, we will use this metadata to resolve conflicts. We will first use the timestamp to see which write happened before which one. The timestamp is a glorified version. Like, let's say I write to region 1 before region 2. Region 2 could land up getting a smaller timestamp, so region 2's write may get clobbered. But it's just a way of like us saying, okay, this is how we're going to do conflict resolution. We use timesync, which is fairly at P90. The drift is very small across regions as well, right? Have we seen time drift like upwards of 3 seconds? Yes, we do see sometimes like P100 of 3 seconds. The thing is that one of the writes is going to get clobbered either way around. So it's not much of a difference which one gets clobbered at that point in time. Right? So asynchronous global tables resolves the write-write conflict with last writer wins. This is one of the key things which is super important to remember about this, that if you're writing to multiple items, if you're writing the same item and from multiple regions, only one write is going to win over the other writes. Right? Now, this has very interesting properties. One is if there is a region which is not reachable or there's a region with a failure, replication to the other regions will continue. Um, Once a region recovers, then replication will catch up to that region. If the replica is down for 24 hours, usually we kind of land up dissociating the replica. This does happen if customers use their own keys to manage the encryption, and sometimes they will yank the keys. So Dynamo can't replicate, in which case we'll say, okay, fine, after 24 hours, we're just going to not replicate anymore, and we're going to dissociate the replica. And also there was a streams limitation back in the day, which was like streams only are persisted for 24 hours. After that, you start losing streams. If a particular region is isolated, it's the same thing again. The other regions are available, and the region which is isolated is also available for reads and writes. It just doesn't get updates, right? It's very eventually consistent at that point in time for writes in the regions which are the other regions which are happening, right? So your applications would not notice there's a network partition or the region is isolated. The applications would continue to kind of work on the respective regions, just that they won't see the writes. They would see the writes after the network partition is recovered. So once we built this and we kind of had kind of global tables going, it was kind of interesting to see how quickly a lot of customers adopted global tables, and how quickly there was a lot of impact on like just disaster recovery as being the scenario. And a lot of other customers wanted local reads, which were really, really fast. And that became another application as well, where customers were looking at reads which they wanted to perform in region and was quite fast. And they didn't mind reads which were stale. But there were a lot of other customers who were like, hey, your neighbors north provide strong, consistent reads. You can read your writes from anywhere. We want to kind of have a global database or global data store which should do this stuff for us. They went ahead and built stuff around DynamoDB Global Tables. They would write to a single region and read from that region, which supports strongly consistent, but they had to kind of keep track of which region this is. This worked for some customers, or some customers even went and did quorum reads, which is like, hey, I will replicate the data like in 5 different regions and then do quorum reads and then read the data and do my own conflict resolution. But all this didn't sound like it sounded like a differentiated heavyweight lifting, which their application did not need to do. Right? We knew that we can go and implement something which they can make use of for reading their own writes. And also, none of this provided a zero recovery point objective for them. If a region failed or a table failed, then the recovery point objective would be like they would lose as much data which was not replicated. Right? So we said we'll go build something which will kind of do strongly consistent global tables. So we call this as multi-region strongly consistent global tables. It's a whole mouthful to say, so I'm going to call it Mercy, which makes it easier for me to kind of say throughout this talk. But the first thing we wanted to solve is we saw log serialization across availability zones. We wanted to solve how do we build service which can serialize logs for us across regions. I know Mark gave a talk here a couple of months ago. I don't know when Mark gave a talk. So both DSQL was also in the oven, and Dynamo was trying to do strongly consistent global tables. And we built something called as we kind of said we should build something called as a multi-region journal. So both of them use multi-region journal as a log mechanism to kind of replicate logs across regions. Multi-region journal spans 3 regions today, the 3 regions in which you have your replicas. All it does is it kind of lets you append logs across 3 regions. And it would only kind of append a log and return a success if it can do it across 2 out of the 3 regions, and then give you a callback saying, okay, the log is appended. Now, you can also have listeners in other regions. You will also need to have listeners from these regions because the logs can be appended by any writer. So you want to listen to all the logs which are appended so that you get all the logs in the serial in the same order as they get appended to multi-region journal. So multi-region journal was built to kind of solve a bunch of the problems which we want to solve in terms of like, hey, how do we not lose? How do we kind of do log serialization across multiple regions? The listeners need to listen because they need to get all the logs in the order in which they're appended, because append can happen from any writer. So if you want to kind of keep track of how do you kind of append how do you make sure that you don't miss any of the logs, then you need to have your listeners listening to this multi-region journal. And the multi-region journal would give the call back to the listeners in the same order the logs were appended, right? And it would give you the log entry. Now, Mercy Global Tables uses multi-region strongly consistent global MRJ to build upon. When a write comes into a single region, first a log is written to the multi-region journal. And once the listeners get the call back saying, hey, there is a write for this particular item, they would go ahead and apply it locally in the region. This is as simple as that. Now, when you perform a strongly consistent read in the region where the write was done, this is very trivial. You can always read your writes in the region, right? So it's not hard. When I perform a consistent read in a region which has not got the write, how do I know I have the latest write? Right? There's no way that region can know it has the latest write unless it knows that it has read everything in the log up to that point in time, right? So the consistent read actually generates a heartbeat to the multi-region journal. Think of it as a read barrier, right? It's going to send a read barrier or a tracer bullet to the multi-region journal saying, hey, I need to know, just write this heartbeat to the record, to the up into this to the journal, and then give me a call back. Give me all writes I've missed so far. So once the heartbeat goes in, the listeners will get the call back for the heartbeat, but they have to to go get to the call back to the heartbeat. They have to catch up to all the writes they've not kind of applied yet. So they start applying all the writes they've not listened to it. And then when the heartbeat appears, you can kind of read whatever item is applied and return back. So this is how strongly consistent reads work on multi-region journals, multi-region global tables. Now, if you have writes happening to the same item in two different regions, the writes would be applied in the order the multi-region journal serializes them to the log. So if there's a write B in region R2 and a write A in region R1, they both would try to append it to the multi-region journal. Write B gets appended before write A. The listeners in all the regions would listen to the write B log. They would write the first update to the item, and then they would apply the second update, which is the write A. This is the strongly consistent read in the region in which you do the write. Also heartbeats today. And we did kind of take this route. It does add a lot more latency for strongly consistent reads because the heartbeat is an expensive operation on the multi-region journal. It's a write is very expensive. Depends on the region set. Like if it's IID and CMH and PDX and you're doing a write and doing a strongly consistent read in IID, it's about like 20 to 30 milliseconds round trip because the heartbeat has to be serialized and then read back. And usually you're caught up to the writes up to that point in time. So it's just a matter of just listening to the heartbeat back again. It's just a heartbeat. We did not take any timestamp into account for that. So you just heartbeat and you just return back the heartbeat. You'll have an identifier with the heartbeat. Yeah, you have an identifier with the heartbeat. You're right. Like because there may be multiple strongly consistent reads you're performing, so you want to know which one is your heartbeat. So you do have the item key which you're trying to read and an identifier which says, okay, this is your heartbeat. So asynchronous replication had the replication engine outside the Dynamo, reading streams and doing a bunch of work. Multi-region strongly consistent DynamoDB tables use the replication which is inside Dynamo now. We just kind of moved the replication piece inside because it had to happen before we can reply to the customers. So write comes to the request router. There's a global table shard processor which is basically responsible for a set of keys for a given table. It reads the latest version of the item from the DynamoDB table, generates a log entry, appends it to the multi-region journal. And the multi-region journal gives a call back to all three regions saying, hey, I've applied this new update for this item. The GT shard processor then tries to write it to the DynamoDB database. If it's successful, then it would return back a success to the customer. If it is not, then it would return an error to the customer. And this can happen because the thing we went for was like deterministic execution. What we said was that if all three replicas started with the same state and had the same set of commands to apply, they should all converge, right? Because the order in which the commands come in are the same. But the commands have to be idempotent and have to be deterministic in terms of execution. So every update we do to a DynamoDB item is converted to an deterministic execution. And how do we do that? We take the current value of the item. Let's say I'm trying to increment a counter. We take the current value of the item, generate the new item, and then say, hey, write this item if it matches the previous version of the item. So this is a log entry we generate, which says, hey, here's the command you need to execute. What this allows us to do is that if two different regions are trying to write to the same item and they're reading the same value of the item from the database, they'll end up seeing they land up. One of them lands up succeeding, the other one lands up failing because they're deterministic execution. Now,
The one that fails is the one that comes second. The timestamp of the second one.
yes, the one that fails is the one which gets appended to the log entry the second. So it does fail. And this is one of the things we introduced. We had a lot of debate about introducing this exception because what Dynamo goes for is like, hey, if you had an application which was working for a regional table, it should work for a global table as well. But just introducing this application meant that customers had to handle this exception and retry the update again. A big difference in Mercy Global Tables is latencies. This is a killer. I will kind of give you a demo on how latencies differ between both async and Mercy Global Tables. But the latencies depend upon the three regions it's a PEC. For example, IID to PDX, IID to CMH, UOC is 20, UOC is 2. The latency is round trip is 25 milliseconds, so it's usually okay. But if you have a write which is happening in PDX, that's going to take a longer time. And likewise the read as well, because like Akshat mentioned, the read gets converted to a write. So all regions are not equivalent. If a single region has issues, then that particular region can't take reads or writes, but the other two regions can take reads and writes. We are fine. There's no issues with that. If the single region is isolated, the single region won't be able to serve strongly consistent reads or writes. It'll be able to serve eventually consistent reads. It's still fine. The other two regions will still work fine because the multi-region journal is its mechanism for replication of data. But the super interesting scenario is a network partition between, let's say, UOC East 1 and UOC East 2. All things will work normally. You would be able to do strongly consistent reads, writes in all the regions. The only reason this is possible is because the replication logs would flow through US West 2 to US East 2 and vice versa. So because multi-region journal, US East 1 will be able to write to the multi-region journal, and that needs only two regions to commit. That's going to be able to use US West 2 to commit. And likewise, in US East 2, it is going to be able to use US West 2. So this is a slight difference. The regions will be still available. You can do strongly consistent reads and writes from all three regions. Multi-region is hard. It's not trivial, especially when you're kind of having an application stack which has to work across two different regions. Region failures can impact your stacks in very different ways. And this is one of the scenarios where all of a sudden, since your writes are slow and reads are slow, you will start needing probably need more compute to scale all of a sudden, because now you're processing smaller number of requests and your throughput of your box itself has gone down, for example, right? So yes, this is something which we talked about last night as well. Like, this is something we should talk about, where multi-region is hard, and the mindset you require when you're building an application stack which works across regions is going to also have to change a little bit, because one, you need to be continuously testing this stuff where regions fail. That's also a very good question. AWS has come a long way. We kind of had where we didn't have this, but now we have experiments you can run, fault injection experiments you can run across multiple services. Dynamo is one of them. Dynamo Global Replication is also one of them, where we say, hey, you can pause replication so that you can pause replication. Definitely latency is one which we should have on our roadmap to add so that customers can experience this latency thing. And this did come up when we were building the fault injection simulator to say, hey, we kind of simulate faults today, but we don't simulate the latency. And this is one of the key callouts we had, is like, we don't simulate latency. But the idea was that we'll add a similar latency simulation later in faults. I just have a small demo here, which I usually give. The demo is two experiments. One is concurrent writes across multiple replicas in 3 different regions. I have a DynamoDB global table which spans 3 different regions now, has 3 different replicas. The table with the asynchronous, which is named async GT, is the asynchronous replication. So the first experiment I'm going to run is like 5 iterations of counters, just running counters like, hey, increment your counter, conditionally increment your counter in each one of the regions. And we're going to see what the value and how the latency profile looks. My TypeScript is obviously horrible, so I didn't get this entirely correct. But as you can see, like, each one of the regions did its own conditional update, and the values are at the end, which you get displayed as basically whatever that region landed up writing. The latency was pretty quick, like, given the fact that I'm still talking from Seattle, the latency to PDX is quick. You can see CMH and IID matches the latencies. Like, this is what Dynamo write latencies would look like. I have the average latencies was about 37 milliseconds to PDX, and IID was 139. I think this is mostly because of the client setup at this point in time, so the average is kind of high. But the key thing here is to notice that each one of the replicas got its own values, did its own update, and they all have converged on 5 at this point in time. So the writes locally were done even before they got replicated. So none of the other replicas even saw the value which any of the replicas wrote before they did the increment. It takes a longer time to finish running this experiment. And as you can see, the counter value is now 15 because I kind of incremented the counter like 5 times from each of the regions. And the counter value is 15. The first update was in US East 2, 0 to 1. The second update was again in US East 2, but then US East 1 got its update through. But it took quite some time. It took around 408 milliseconds. Is just because if US East 1 tries to update, and the update fails, you get a conflict exception, and that conflict exception is retried. So we can see that whenever it's getting a conflict exception, it's going to take a lot more time to kind of get the next update through. And finally, the value in US East 1 converges to 14 to 15. All three replicas would converge to 15. I should have done a read at the end, but I was lazy to kind of get that done. But but I have another experiment which actually does show how the reads work. In this experiment, what I did is that I wanted one replica to continuously write and the other two replicas to continuously read the values of the DynamoDB table. So I chose to write to US East 1 and then asked US East 2 to do strongly consistent and eventually consistent reads. As you can see that when I did the writes to US East 1, I've been able to write to 5, and US West 2, after even like 10 iterations for a second, it did not get the value 5. So the value 5 was not replicated here still. But US East 2 got the value 5 replicated, so I was able to see the value 5 in US East 2. So you can see that when I'm reading from US East 2 and US West 2, US West 2 doesn't get the latest write. So this is where the whole eventually consistent writes reads work for you. Well, asynchronous replication work for you is kind of the thing with this one. And with Mercy Global Tables, I'm going to do a very similar experiment where I'm going to have one replica do 5 updates and the other 2 replicas continuously read for a second to see what the values they see are. They're doing both strongly consistent and eventually consistent reads. You can see that US East 1 does apply up to 5. Both regions are able to kind of, when they do a strongly consistent read, they get the latest value. The eventually consistent read, for example, in this case, did get a value which was local to a replica, which was not caught up to the leader or was not caught up to whatever the multi-region value was. In US West 2, one of the replicas is lagging behind, but eventually they catch up to whatever the value is in US East 1. The latencies here, as you can see, for the strongly consistent reads are almost similar to the writes. And this is one of the key things we were talking about as a read gets converted to a write and requires the multi-region journal to kind of replicate that heartbeat, replicate the read barrier. This is a matrix of difference between asynchronous global tables and multi-region synchronous, multi-region strongly consistent global tables. I won't kind of bug you with this. I think the key difference is the network isolation and network partition and how both these tables behave, and that might be the only thing which is very different between both of them. And then the latencies. The thing I wanted to get is like multi-region mindset, which is something which is very different from a regional mindset, because in a regional mindset everything is almost constant and everything is almost predictable. In a multi-region, it's kind of the mindset itself is hard. You kind of have to kind of think about how you're planning to use multi-region. How are you kind of going to test this always? How does your restore, like for example, if you're using backups, restore from your backups regularly, fail back, fail over, because you need to know when you want to kind of fail over to another region, whether everything is working, your credentials are working, or every other system is working, because it's just not going to be one part of the service which fails. When I think about multi-region, it's just not about like, hey, is a customer going to flip over just the DynamoDB, right, reads and writes? I think about an entire stack switching from one region to another region, because most customer stacks work within a region very well. It's isolated to a single account, and it's better. The other thing is test system invariance. We place a lot of emphasis within Dynamo replication and storage to test the system invariance and correctness and availability overall within the storage area and the replication area. This has helped us a lot. We use TLA players and formal modeling tools like P to kind of constantly check the correctness of the system. When Akshat and I were working on transactions, we built a transaction acidity verifier, which continuously takes the replication logs and verifies whether every transaction meets all the system invariants we kind of set for it. We also think about systems. When we build systems, we think about systems which we would drive developers to use it as an active design, because pushing the big red button is a once in a lifetime thing or once in a decade thing, whichever way you want to look at it. But that day, it should be easy for us to push the red big button. And it's easy if it's an active system, because then you don't really have to worry about like, hey, if I fail over to another region, whether it's going to work or not work, right? So the multi-region mindset is super critical for anybody who's like developing multi-region applications or multi-region services. That's all I had. If anybody's interested in P modeling or P checking, P observe, which we use today to model our replication protocols and verify its correctness continuously, I think you guys should kind of check out P. P is really useful. The nice thing about P is that it lets you it keeps your code almost identical to what your production code is going to be. No, not Rust code. Rust is a different checker. I can put you in touch with that. But at least for Java and a bunch of other programming languages, P is really good. It lets you kind of keep your code almost close to what it would look like. P Observe is another tool which basically lets you kind of check the logs and check correctness just using application logs. So you don't have to worry about writing the invariants in code.
For replication, conflict exception, I think was close to what it was called. Do you throw that for any conflict at all? Like, for example, an increment. Like if you're just trying to increase the value of a number by 1.
Yes, we do throw a replicated write conflict exception for any 2 concurrent writes happening to the replication log. We could have optimized it for condition checks, saying, hey, condition check failed. We thought it's simpler to kind of implement replicated write conflict exception back if we see 2 concurrent writes.
Is that true also even for operations like trying to put an extra element into a set or something, a string set? You could imagine that they don't conflict semantically and that they would converge in either order.
Yes. So both DynamoDB Global Tables do state replication and not operation replication, just because it confuses. When you want to replay it, it's very confusing. If you're trying to replay operations, you exactly have to replay all the operations to get to the current state. It's easier to do state replication and have the state replicated. So yes, if you're adding an element to the set, it's a different state. And if you're adding the element to this set, it's different. Though I think in Synchronous, we did solve the problem using CRDTs, which I think is cool. And I think Dynamo should, at some point in time, implement CRDTs, and that's easier to do that. Yes, I think that's a good idea.
Can you go back to that heartbeat read slide? So where we are writing to the multi-region journal and then you fired a heartbeat. So if I understand this correctly, so you fire a write A in this case, right? First in region 1, and that write A goes to multi-region journal, and then multi-region journal fires a callback to all regions saying that apply A.
Yes.
And then when the consistent read comes to region 2, what is the exact sequence of steps? Like it triggers a heartbeat to the multi-region journal first.
Yes.
And then what is the sequence of steps after that?
So it triggers the heartbeat down to region, multi-region multi-region journal, which the listener in region R2 has to pick, right? But the listener in R2 can only pick that heartbeat if it's applied all the writes before that. It cannot deliver that. It's doing all the delivery of all the logs which are appended in serial in which it listens, it gets the callbacks in, right? So it would get apply A. If it's not got an apply A yet, it'll do the apply of A first, right? And then it would say, hey, heartbeat, it's your turn to read the item. Now you're good to go read the item. And you can now go to the leader to read the item.
So a couple of questions in that. So how does it know it is apply A or apply B it has to look for? Is there a hash-based search?
No, it doesn't. It doesn't care. You might have not even written to the item the consistent read is reading, right? But to just maintain correctness, it has to apply all the logs to know that there's nothing there.
What happens to the client during that time? Like client receives...
Client is waiting. That's why it takes like 200 milliseconds or like 80, 90 milliseconds. Like most of the times when you do a consistent read, the difference between a consistent read and a write, the latency is not much. Like especially if it's like an 1 kilobyte read and write, it is hardly anything because the heartbeat has to circulate through the multi-region journal and you pay that cost. We could have switched very easily to what the protocol is. So when we built this protocol, we did give leeway to build a zero RTT read, where you can do the local read consistently and hold on to the commit, just like what DSQL does, where DSQL says, hey, commit this in future, and I'll make the read wait until that timestamp and make sure I've caught up to all the commits. It's not very hard for Dynamo's protocol to change, but we thought, okay, this is a better thing for our customer experience overall to kind of have reads be the same latency profile as writes. And customers are all over the place as far as if you ask them, like, hey, what read and write latency profile you want? It's like, they all wanted strongly consistent reads.
Even in R3, it would do the heartbeat to get the latest zones.
RT would also listen to the heartbeat. It'll ignore the heartbeat. It'll say, hey, this heartbeat doesn't belong to me, and it'll ignore it completely. So yes, you're right. The heartbeat is also a callback to all three regions because it's written to the journal. The journal doesn't know what is being written to it. The heartbeat is just a record in the journal, like saying that, hey, this is a read barrier. It's a read barrier for a particular read in region in this case, right? So R2 would get it and ignore that record completely and say, hey, I don't have anything to do with this record.
This is just a hypothetical scenario, but like one of the apply could drop. Then like by sending from journal to R2, if you send like, oh, there are 10 different apply which you need to do for A, and one of them gets dropped or something, like is there a way to do some kind of verification of
This is Akshat's favorite topic, so I'm going to say yes. I think one of the things we land up doing across all global tables is run anti-entropy in the background all the time to quickly detect any convergence which are not happening between the three replicas. And this one is even more serious because if the apply A gets dropped, then everything else is going to kind of stop working after that. So yes, we continuously keep checking all three replicas for convergence.
If things were starting to lag, it seems like that would be bad. Especially like with I mean, even your reads are going to start to just you'll see latency, right? Latency on your reads and your writes. Like, what do you do about that? I mean, and there's a couple. Like you could have one region. I don't know. It depends what's going on. Like if the multi-region journal seems to get kind of clogged up a little bit, it could affect everything. It could maybe just be the one region getting stuck somehow. I mean, to some extent, we're just like trusting you guys, but also like we care a lot if our latencies start to go up. And are interested to kind of know like what are the bounds, what kind of expectations should we set for like tail latencies on these reads and writes, that kind of thing.
Tail latency is a very tricky one, especially with multi-region global tables with strongly consistent, just because you need two regions. And like you said, UOCs 1, UOCs 2 is like 20, 30 milliseconds regularly. But once in a while, you'll see a blip of 200 milliseconds just happening just that way. Right?
Mm-hmm.
We closely monitor it to make sure that it's not a sustained event and it's just a blip in one or two operations where the tail latencies go high. So we do closely monitor it. Definitely, we could kind of move the read protocol away from the heart beating so that read is like way faster than what the write is.
What about like non-network issues though? Like, so internet fine, like I get that. That's easy. That's totally expected because like I've sent lots of traffic across the country. But like, what about other things like whether it's, I don't know, operational stuff, whether it's just like a noisy neighbor or somebody just jams a bunch of traffic in or a deployment that goes south, right? Like somebody deploys some code and it just like wasn't perfect and there was a little tiny glitch. That's probably going to be one of your most common things.
This is one of the things we talked about as the multi-region mindset, right? How do you think of deployment across regions, right? Because now it's not that the customer is just dependent on that one region and one availability zone deployment. It's cross-region deployments as well. And there's a lot of emphasis placed on like, hey, if IID, PDX, and CMH are your core regions for a multi-region global table, or most of your customers are using within the US that global. Then you deploy to CMH, wait for CMH to kind of stabilize over a period of time. You can go deploy some other region, because you kind of stripe regions in that way, as opposed to saying, okay, after CMH, you can go deploy to IID. No, there's a lot of emphasis placed on like how are you deploying to the stacks now, right? Especially we don't want to take down like if IDPDX and CMH are like dependent regions, we don't want to kind of take down two, because we need at least two regions to have the commits happen.
So I'm kind of curious from like a deployment and testing perspective, because you're deploying you're deploying to like different regions, right? And so at different times. So how do you sort of model like version inconsistencies, or is your protocol just like stable?
A lot of this is baked into the design of the protocol itself. Like when you think about the protocol, we think about like, hey, how do we make sure that its protocol is upgrade safe? Yes, right. For example, if there's a change in the write schema, then we would kind of make sure the readers are running up and front before the write is done. Even when we're building transactions, this is one of the key things. Is like our protocol is upgrade safe, because it's very localized to the transaction coordinators and what the storage nodes talk about, like whether they say yes or no. There may be an availability impact, but correctness is of paramount importance for us. So we always kind of bake that into whatever protocol we're designing.
This looks like more like Paxos, right? I don't see any difference.
The multi-region journal is a variant of Paxos. So was Dynamo regional replication is a variant of Paxos. So what multi-region journal does under the covers is a variant of Paxos. That is no questions asked about that. But Dynamo itself is just using the multi-region journal. It's just doing deterministic execution on top of that. So
Like C reads are basically going through Paxos.
to the journal, yes. It's like basically a read fence saying, hey, I want to read, but I want to read all the writes before this fence.
Why can't like multi-region journal, when the nodes get the updates, do they just give it to the data nodes from the same region?
No, it's just an abstraction on top of it, right? They don't know that who's doing the writes. This goes back to like, how do you think about like protocol version update and everything else? Like they don't know about the storage nodes or anything. And the storage nodes in two different regions can have two different set of keys. So the GT shard process is just a compute node on top. It says, okay, when I get a write or I get a read, I will convert that and write it to the journal. So the journal can independently scale from the storage nodes and the compute nodes overall. So, thanks, guys.